All right. Anybody else? 3 examples. Yes. Janice? Okay. Okay, good.
Yeah.
So, very simple, right? So you have an A followed by a number of pairs of A's,
Yeah.
right? And the whole thing repeated twice. Can we put 2 different? So you see, this 2 represents number of repetitions, right? Can we put different repetitions?
Yes.
Yes. Let's try one. Okay, thank you. Next one, but don't repeat the same string. Pardon?
Okay, I mean, it can be also this tree is a group, so it's.
Go on time. Go on time.
So it's size different. So it's A is a group. So and repeat 4 times.
Yeah, that's true. So I was trying to say don't repeat.
But it's not even one A.
Oh, okay. All right. Anybody else who would like, put clearly non-repeating patterns for that 2 there? Okay. You are
From Zofia.
Zopian. Okay.
Can I delete them?
That's right. Right. So show exactly the separation. Where do we measure the first time? Where is the second repetition?
Well, that's...
Yeah. So the way they are separated now, the first string matches one instance of the regular expression, and the second string matches a second time the same regular expression, right? Is it clear? So we don't have to repeat the same thing. Every time we start matching this regular, so this regular expression, let me show you so that it's recorded, right? So this regular expression has to be matched between 2 and 4 times, right? The first match and the second match don't have to be the same strings. So, right, what you see here is that this is the first match, which is perfectly valid, and this is the second, starting at this A, is the second match. Is this clear? And you can do it 4 times, right? So you can have another A, B, A, for instance, right? A third repetition, and A, a 4th repetition. And somehow it doesn't work. There is a reason why it doesn't always work as expected. It's because the regular expression library that is linked into Ruby has a greedy approach to matching. It first matches as much as it can from a regular expression, and then it looks for the alternatives. So sometimes expressions that are valid actually are not matched and have to look for alternatives. Okay. All right, let's look for another one. Yeah, that's right. Okay, who wants to try this one? 3 examples here as well. Your name? Jeff. All right. Okay, good. So explain what matches what.
The first A matches the first
Bracket.
brackets, and the last
sequence of D matches that D question mark.
Okay, good. Anything else? Anybody else? Yes.
So you just need to change A to B, C, still match.
Okay. Good. Got an example? One that has ease.
It won't match E.
It won't match E. Why?
The D is going to match 0 or more 1 times because it's greedy, so it just match D.
So it's the greediness of the library that makes ease not acceptable, right? So this is one instance where theory and practice do not match. If I say BCE, the E won't be matched. Why? Because the empty string that appears between C and E matches D question mark, right? So the library says I have matched the entire bracket now, and E is outside. I can't be bothered to look for more. If we go here, and so clearly by theory E should be accepted, all right? But the thing is that we can always change the regular expression, right? Regular expressions are not unique. We can always change the regular expression in such a way that we can get what we want, right? So if I delete the question mark, then I can put here as many E's as I want, and I can get them matched. Yes?
Regular expressions in general for all implementations?
No, it's no. So as far no, not true, not true. Not all implementations are. So you will find out there implementations of regular expressions that, especially if you look at Java. Java has a regular expression library that will have flags that will match properly, even though that will be less efficient. But there are implementations out there that work that way. However, this is a very old issue. It was implemented like that for the regular expression library that was created for grep, for the grep command. Right. So when they created the grep command, everybody knows what grep is? No, huh? So it's a Unix command, which you can have in Cygwin, which we have in Cygwin as well. Which looks for a string that matches a given regular expression in a file. I don't know why it takes so long. This is since I reinstalled it, it takes ages. Let's look where we have some code. So there's some prologue. Right, so for instance, with this I can do grep, and one thing that I know I'm going to find for sure in a prologue file is this colon minus, and I can look in all the files.pro, and I'm going to get a list of all the lines in a file that match that regular expression. We can also see that, for instance, the string append it appears quite often. So let's put a regular expression here in the form of AP question mark dot star. Dot means any character repeated any number of times and followed by a D. Okay? Oh, and we don't find anything. Does this work? Oh, 0 or 1. That's true. That's true. So let's put a star here. Let's put a dot star here. And turns out balanced works in the same way, right? Yeah, because balance has 0 p's and an A and a D. So the P star there actually doesn't solve a lot, right? So we can ask here for 1 or 2, which is, we can do it this way.
I think the way graph needs the expression, you have to put a slash in front of the bracket.
That's right. Okay, so the syntax is, yeah, that's because the command line will treat brackets, the braces, in a way that bash will have its own interpretation for brackets, so they don't have to escape them. Okay, so that's what grep does, right? So that was the first implementation of regular expressions in the world of computing over the last 50 years ago. And that library stayed with us ever since. And it's linked into many, so all the programming languages, Perl included, right? So Perl is another example of a language that has regular expressions as a mainstream or object. Also relies on this library to perform its checks. One interesting issue that we're seeing here, and maybe we should experience firsthand as well. What you see here, this IRB, is the interactive Ruby, right? And the way we play with regular expressions is this, right? So a constant of type regular expressions, regular expression is given between slashes. So A, B star C would be any string starting with A, ending with B, with C, and having B's in between, any number including 0. Right? So this is a regular expression. It's an object. All right? And I can call from this object a method called match, and I can check whether AB, for instance, is a match. And, oh, it's not. AC should be a match, right? So we can see match data. So that's another object, right? And this object can be changed to string, I hope. This is the, what's the toString method in Ruby? Small s. Yes. Right, so the match data can be changed into a string, and you see the string there, right? So notice the fact that this, which is, I want to highlight, is in fact a constant of type, regular expression, right? You have constants of type integer, constants of type string. Right, for numeric types, we have a lot of types of constants, real constants, infinite precision constants, and so on, right? So this is one of the few languages where we have constants as part of the mainstream part of the language, constants of type regular expression. And we would have objects of type regular expression as well. Questions? So far. We actually have several, we have one more here, right? So let's try to solve this one in Ruby directly. So I'm going to bring it here. So somebody can come and in the between the double quotes write a string that matches that regular expression. Your name? Sonia. Yes. Okay, so the entire string appears there, right? Because the match command will try to match any substring, not the entire string. Thank you. Okay, anybody else? Second example? Yes, your name? Jiangshan.
Something wrong.
So A, D, E, A, D, D, D. No, you can't have multiple E's.
Oops, okay.
Just one. Okay, very good. Okay, and one more. One more example. Yes, go.
We have
Okay, good. So like everything is there. So actually, if we don't use the 2s, we're going to see what is left out. Right? We see all the matches in sign. Right? You see that the first match is the entire string. There's a second match, which is ADE. There's a third match, which is AD, and there's a fourth one, which is just A. Okay. Clear? Okay, let's go and see exercise 2. So for the second regular expression exercise 1, define a DFA that accepts the language specified by it. Let's see if the following works. Doesn't work. All right, so we're going to have to draw on this side. So who wants to try to draw? It's relatively easy. Control Z will delete, undo the last thing. Yes. Either. So if you're going by the theory, either should work. And maybe we will understand why it is difficult to implement. So let's say this is a state, call it something like 0. And
yes.
you want that to be the final state. That's D.
Erase.
And E.
Can erase.
Control Z will erase.
Oh,
Last
never
name.
mind, it's okay, right? Oh, yeah.
It's good
Okay,
now,
yeah, that's a D.
It's good enough.
Mm, yeah.
Right? So notice now that the question mark, what would the question mark do? No, we can't have another state. The D can be there or not, right? So we either take the transition or we don't take the transition. Pardon? Yeah, you can have another self arrow, right? With the empty string, but then it's not a DFA anymore, right? Then you don't have a DFA anymore, right? So normally the theory says the following. Okay, thank you. This is a good automaton. The theory says the following: that every regular expression can be converted into an NFA, non-deterministic finite automaton. Non-deterministic finite automaton has multiple transitions from the same state to multiple states, and also has epsilon transitions, has transitions on the empty string, right? So I can have something like this, epsilon. All right, and I could have an epsilon here, but I could have an something like a, so two transitions from the same state on the same symbol to two different states, and let's say between this I can have an epsilon transition. Okay. However, the conversion between, so that's what the theory says, that every NFA, so the blue one is an NFA, non-deterministic finite automaton, can be converted into a DFA. They are perfectly equivalent. However, the conversion takes exponential time and may increase the number of states exponentially. That's the reason why the regular expression library does not perform this conversion. Right? So the conversion is always possible. You can take the regular expression and produce a DFA, right, which is easy to implement, and it will necessarily not be greedy, not have the greedy problem. But that conversion internally may take exponential time in the number of symbols in the regular expression and increase the number of states exponentially as well. So that's something that they avoid. So they use a heuristic. They sort of process the regular expression directly in order to try to match it, and they're trying to be greedy at all times. So as soon, if you have an alternative, for instance, right? If you have an alternative, as it is the case here, they will try to match this one first. And here they will always decide, oh, well, the empty string that I have in between any two symbols is a match. Therefore, I have already matched this expression, right? An infinite number of times. So I don't have to look at the E. Whereas, if you convert this into a NFA, this epsilon transition will definitely not exist. Okay? And whenever you see E in your input, E will be considered part of the matched string. Okay? So try to remember that. On the other hand, it's also always possible to tweak the regular expression in such a way that the greedy problem does not occur. Is this clear? Yes.
This diagram is correct.
This diagram is correct, without the blue arrow.
Does this mean that when I'm in state 2, I can accept the E?
You can accept any number of E's. Yes.
I can, but this is not what the regular expression accepts.
Yes. Because the regular expression implementation, the regular expression library, is not a faithful implementation of the theory.
Oh. So we're just trying to do something that's faithful to the theory and not.
Whenever I'm going to ask you draw me the DFA for a regular expression, yes, I'm expecting the one that's actually the easier one to draw. You're going to have to draw the DFA that, according to the theory, implements the regular expression. Okay? Not the one that Ruby would accept. So Ruby always will accept less. That's what you have to understand because of this strategy. So it's not more permissive, it's less permissive because of its greediness. Is this clear? All right, next one. Let's try a regular grammar. For the same regular expression, let's see if we can keep them on the same page. Maybe we can make them a bit smaller. Okay, so this is just to create a lot of white, so it's easy to see. So what we want now is still use this regular expression and have a regular grammar, which we want drawn on this white space. Who wants to try? So let me remind you the DFA, because that's essential. Right, so the DFA we came with is we have a state which we call 0, and then we go to a state 2 on a symbol A, and to state 1 on symbol B, here on C, then we stay here on D and E, and this is also a final state. Okay. So, regular grammar. What's a grammar? Discussed in the last lecture, right? It's a mechanism for generating grammar, for generating languages. So if I perform an enumeration, which is relatively easy to do by the production rules, of all the strings generated by the production rules, I will get eventually all the strings in the language. Who wants to try? Yes. Okay, good. In general, we don't want to have grammars with epsilon productions, but yeah, that's fine in this case. So, how does a grammar work? We start from the start symbol, just to understand exactly why this is useful, right? And we build a derivation tree. So I can use either of these production rules, whichever I want, to perform a derivation. So let's say I use the first one. Okay? And then this, whatever is the fringe of my current derivation tree, is the frontier of the tree. And I can identify more non-terminals and perform further derivations, right? I can pick for A any of these three rules. So let's say I pick this one, DA. And then I have another A here, and let me pick this one, right? So I have EA. And then finally, let me pick this one so I can have an epsilon. So when I have no more terminals on the frontier will give me a string of the language, right? So it's a mechanism for generating strings in the language. It's a very convenient mechanism because it captures the structure of the language. So this is how we want to define a language usually, by its grammar. All right? Now we should have an equivalence between generating mechanisms and accepting mechanisms. So in the case of regular expressions, which the regular expression is also a generating mechanism, right, we should have an equivalence. But the equivalence is via the automaton, the DFA. And how do we do that? Well, we have a start state. This is the start state. So the symbol state, every state gets a non-terminal. This one gets 0. This one gets 2. A corresponds to 2. C corresponds to 1. Okay? And every rule of the grammar corresponds to a transition. So this transition corresponds to the first rule, right? From initial state S, I can accept the symbol A and move on to the non-terminal A, to state A, right? Or from state S, I can accept the symbol B and move on to state C, right? From state C, I can accept terminal C and go to state A, and so on and so forth, right? And now it's very clear how it works. So each state gets a non-terminal, each transition gets a production rule, and for the non-terminal that corresponds to a final state, final states we don't need to have just one, we may have many, right? We add a production rule that non-terminal derives the empty symbol as well. Okay? Is this clear? It's going to come up in the exam, so better clarify now. Are you able to get into the? Actually, I am on wireless on this one. I don't know why I can't log in from the other one. Clear? All fine? Yes.
Can we define its grammar in BNF?
Yes, sure. Yes.
Okay.
Whichever you like. All right, so let's write a little C program that implements the automaton equivalent to the regular expression that we have discussed. So how would we accept a string? Who wants to try this one? Come on, it's not that complicated. Yes, Joshua.
Code blocks.
Yeah, code blocks would be good.
Code blocks.
I haven't started it yet. So we've seen the automaton. Right, what we want is a standard implementation, sort of. What are we looking for? So tut03 for its G1 put to a group. And we're going to do what we call a standard implementation, even though, because the current automaton is very simple, you might think that it's an overkill. All right, the standard implementation for an automaton has a switch for states, and inside every case, there's a switch for the current character. You don't need to do that. Yeah, so state equals 0 is good. You don't need to say which is final either. Right? So we're going to have while s star s not equal vector 0. Vector 0. Vector 0. Right, and inside the while we have a switch state, right, and we're going to have how many? 3 cases, right? Case 0, case 1, case 2. So for case 0, switch. Switch star s, and we have star s, and we have case character A and character B. Right. So in each case, we have to say which is the next state. Right. So for A, state is I think 1, and break. Don't forget to break. And then in case B, state is it? I think it's the reverse, right? It's 2 and 1. And then again break. And then default. And we should indicate an error state. So default should go to state 3.
Oh.
Yeah, put
Should
state
just
3 and make a centralized decision.
Okay.
And similarly for 1 and 2. Now, we're not bothering to define, so you may wonder, why do we use constants directly? Why don't we define symbolic constants? Why don't we try to be more software engineering friendly? Because this kind of programs are actually generated automatically. We don't have DNA, right? We have DNA. We have DNA.
This is the second.
Oh, DNA, yes.
Yeah.
I'm sorry. So you can say what the next state is again. All right. At the while loop, also say so star s not equal to vector 0 and state not equal to 3. Right. So as long as we're not in an error state, so at the while condition, as long as we're not in an error state. Right? So as we come out of the while loop, now we have to make a decision depending on the state. So if the state is the final state, if state is equal 2, then we return 1. Otherwise, we'll return 0. Right? So 1 means acceptance. And now we can write a little main program to verify that our program is correct and call accept with some string. So I was saying these accept of a function like accept can be generated automatically by a lexical analyzer generator such as lex. Lex is their standard Unix command. Alright, so for each of them, you can also try a string S3. So for each of them, print the result, right? Don't just call them.
Oh, yeah. The
Maybe you should try to copy that.
no.
What's missing? Solve it, it's an
Yeah.
interview.
Okay.
What's missing? Most basic programmer's error.
This one? Default? Oh, yeah. Right.
S++, right?
Uh,
Point of that move forward.
let's see.
Yeah,
That's no. S. Just S.
Okay, so we get the expected results. Very good, thank you. Okay, questions? So you'll probably at some point learn about flex or lex, the lexical analyzer, the lexer generator, and that program does exactly this, right? Takes a regular expression and generates a function in C, and you can go and inspect that function. You can go and open the C file that is generated and look at it, and you'll see exactly a function with a lot of switch cases, a lot of cases. flex will actually not suffer from the greedy group activity. So we'll perform correct matching. Questions? All right, if not, next one should try and match this code. So let me close this project. So now we want to use this code, right? So I want you to do the following. We have 4 places where you can fill in, right? So the ... here, right? And then this empty brace. And you should get the program accepted. You should get to implement the same regular expression. So once, right? So this time we use the same code, but just different data to implement a different DFA. Yes. Yeah. So it's clear that
3, 8. Which one is final? Oh boy. Do you have Vim? Crap. Do you have something that can generate numbers?
so. Let's be slightly smarter. Let's.
ECC extensions.
Yes, so that's what we want to do. So we want star s minus character a. Go to state. The first the inside while minus character a.
Okay. This one.
And then m can only be 5, right?
5?
A, B, C, D, right?
Oh, okay. But if you want to reject characters, if you don't take into account the other characters you.
That's right. Okay, we'll make a change for that. Yes. Just make your say 5, and then let's fill the array with.
A would be state 2, B would be state 1, C.
All right, so inside the while loop, say if, right, so star as
If
you will have,
greater than
larger than E and smaller than A, and smaller than A actually. Say state equals -1 and else, yes. Actually, you don't want to do that. You just want to do the
right, sorry.
the array assignment.
Right. 35. Okay.
Actually, we can go and copy
right.
main from the previous one.
Tutorial. It's not there.
Oops.
Is it here?
03.
We call it tut.
Touch that.
That one. No,
Yeah,
that one.
Okay.
And copy the main, which should be the same.
Okay.
Sorry, I copied it from Acrobat, and surely there are some. Usually the minus is.
What?
At 913.
Oh, right. Actually, you don't even need that, right? Hey.
Okay.
Was it running? The correct one. Okay.
Okay, good. So this is the second way, the second step implementation of automata, right, with a table. Is this clear? Now, the main use of regular expressions is in building parsers, right? So parsers have a two-tier implementation. There's the parser proper, the the syntactic analyzer, and underneath, the layer underneath is called the lexer, or the scanner, the lexical analysis layer, which is implemented as a finite automaton. It's essentially a regular expression-driven parser. And when performing parsing, we want to perform certain actions. Like, for instance, whenever we detect an identifier, we want to put the identifier in a symbol table so that later that identifier can be assigned an address. All right? And because we need these actions, it's typically more convenient to generate it as code. Okay? So going back to this, and you'll see that Lex, for instance, so Lex will implement in this form with switch cases, and you can declare actions, and the actions that you declare will be inserted by the Lexer at every case, right? So you can actually specify actions as C code, and that C code will be literally inserted at that place so that it can be executed. And this kind of approach is more difficult with a table implementation. Okay? So in practice, the switch case one is preferred. Okay, this is it for today. If you want to stay around and chat some more, by all means do it. Yes.
question.
Sure.
Yeah, so you were mentioning lex. So we heard this thing that's called bison and GIEC. So what's it for?
So you can build parsers with them. Let's see where I have an example. I need to save this. Not very sure how. Wait, I don't lose it there. All right. So an example of compilers. Let's go to the last years. All right, so this is a lexer for C. Okay, so in principle, these are regular expressions that define elements of the C language. Let's see exactly what they are. So D is digit, L is letter, H is hexadecimal. So an identifier is a letter followed by letter or digit star, right? And then this is the action that you want to insert in the code. All right, so this is the regular expression. And from this file, Lex will generate a piece of code, which I can show you as well. Which I can show you as well. Let me be sure. Is it this one? No, this is Bison.
Lex.yy.c.
Lex.yy. Oh, so this is the scanner. And do you see the switch? Right, uses go-tos. Oh, okay. Right, so this is the switch. Right, it doesn't generate very readable text, but anyway, so right, it generates a lexer, right? And then this is actually part of a full package that has that also has a parser. Okay. Oh, what happened? Which is in the Y file. Right, so this is the parser. And these are grammar rules, right? These are the non-terminals. Something that is a non-terminal, and this is not Bacchus now, right? So this is the arrow, and this is the right-hand side, which can be other non-terminals. So these are non-terminals, and these are the terminals, which are quoted typically, or they can be non-terminals of the lexing grammars, right? So this identifier is seen as a terminal at the level of this grammar, but in fact is a non-terminal of the lexing grammar, of the lexer. All right, and from all this you get a program that accepts a C file. So it says yes or no, whether a C file is correct or not. So these two files, each of them you have to run them through Lex and Bison. So this one you put through Lex, and it will generate this file, and then this one you put through Yak, and it will generate this file, right, together with their corresponding h files, and then you can link them into a compiler, right? So this homework for the compiling for the compiler class is actually writing a small compiler for a C-like language, right? So I'm giving them the parser because parsers are difficult to build from scratch. It's very easy to get it wrong. So I'm giving them one that is ready-made, but they have to tweak it a bit. So there are some tweaks that they have to make. Yeah. If you want, I can send you this entire thing. It has a right. It sort of explains what you do with these files. Right. These are the commands that you have to run to get the parser running, and then each of the problems will ask for a small change that has to be implemented as a tweak in the parser. So you get a bit more. Right, so essentially you see you obtain an exe file, an executable, and you get some C file like this, right? And it will say accepted or rejected. So that's their first thing, and then they compile. So they already implement a compiler for a small language which looks like this. Right, this is the language that they have already implemented, and they have a compiler for it, right? And then to give it a realistic bend, we take a C file and move it to this language, which can be further compiled, and then you sort of obtain a compiler for C. So I can send you this, and then you get to see in principle what Lex and Yak do. Right? Lex is the same as Flex, and Yak is the same as Bison, essentially. The new commands are useful. Okay.
Can you send us?
Sure.
Email?
Sure.
You need our email address.
I know both of you. Now I know both of you, so I'll remember.
All right. Thank you.
Okay. Don't worry.